Hi, this is going to be lab number 8, flip-flops and timing diagrams.
So here's the circuit that we're going to build this week, and this is involving flip-flops. So we have this new component, and we're going to be getting into the function generator again and looking at the output on the oscilloscope, because this is time-based digital logic. So these flip-flops that we're using are going to be JK flip-flops, which come in the same kind of package as we've dealt with before for the NAND gates. So this package in particular is the HC109. It looks almost the same from the outside as the NAND gate packages, but on the inside, instead of 4 gates like that other circuit, this one contains 2 flip-flops. So this is from the data sheet. You need to have one flip-flop basically hooked up entirely with one side and the other flip-flop hooked up with the other side. It's possible to clock each one of them separately, so really think of it as 2 completely different devices. The only thing they share is the ground and the high voltage VCC. So that's how you set up your relative voltages for the logic levels on the chip. So we can get to wiring this up and testing how the flip-flop is going to be working. We've got nicer wire cutters this week, which actually have the gauges of wires that, the gauges for the wires that we're going to be using. So let's give this a shot, hooking up some of the things on the circuit. For all of our circuits, you'll notice that we don't have VCC and ground shown on this diagram, but we do need the ground always hooked up to 0 and VCC hooked up to the high rail. And we need both the not preset and not clear inputs hooked up to a 1, so that we're not presetting things and we're not clearing the output. So we'll hook up a lot of high lines to each of those things. So let's get things going here. So we need to go from VCC up to high, so we need a pretty short wire for that. So we clip off what we need, and this particular wire, I believe, is the 28 gauge. So you go in the second spot here, and then just strip that off. Now you can bend that into the spot that you need. So we've got our highs on the don't clear and don't preset for flip-flop number 1. We've got our VCC, we've got our ground, we've got our rail voltages hooked up, and we've got our voltages to the inputs here to the circuit. Next thing we're going to need to do is look at what's going on with the function generator. So here's the function generator that we've got. We've got the output on the scope here, and if you look, right now we don't have it on the regular high input. We can go over to that, and it's put on a square wave, and the square wave is going to be dropping from a negative voltage to a high voltage. You could fix that with a DC offset, but there is a default setting to get the right pulse out for digital logic, and that's this one, pulse out TTL, on this particular function generator. So this is outputting, you'll notice, a square wave which is already offset from 0 up to some high value. Now you do have to be careful that the voltage on this is high enough to actually trigger your logic, and we'll talk about that. Basically, this is going up to, you see, up to a voltage of 2.7 or so right now for this particular function generator. So with 2.7, that's probably not enough voltage to count as a high voltage for the clock cycle if we're using 6 volts. So for that reason, we've got our DC power supply set to 4 volts now, just to verify the functionality of things. Okay, so what we need to do is hook up the DC supply and then hook up the clock pulse. So I like to use yellow for the clock pulses here, and that's on pin number 4 in this flip-flop. And for that to actually have the right kind of signal going on here on the scope, what we need to do is also hook up the ground together. So make sure that the ground of the function generator is shared with the ground of the scope. Let's take an input here and demonstrate what we're talking about with that. So you have to be careful with scope probes. They often don't end up going back into they kind of end up twisted at the top, and then they don't end up in the plastic part. And that means that they won't clip to wires and actually hold them very well. Okay, so you don't want to ever move anything with a scope probe. Scope probes are pretty fragile. So we can try and fix that. Okay, so let's just have a look at the clock here. So we do have an okay signal for that. In order to see what the signal is and make sure that everything's grounded together, we do want to have the ground shared. While the scope is hooked up, it can be sharing ground through itself. But just for good practice, you want generally to have the grounds hooked up from both your DC power supply and your function generator so that they're sharing the same thing. Okay, so now let's look at the output of the flip-flop. That's on pin number 6 here. And what it's doing is sort of variable right now because we don't have the J and K hooked up. So we can put it into a toggle mode by setting the J input to a 1 and the K input to a 1. But since this third pin is not actually K on these chips, it's K bar, that means we need to set that to a low so that K will be a 1. Right? So now, as you can see on the scope here, we've gone to a very low time, we've gone to a very low frequency so that we can see things happening in real time, and it's basically just scanning. We've got alternating between low and high with the flip-flop. So the flip-flop is this line here, and the clock pulse is the other one that's changing a little bit more frequently. We can move those apart and just look at the two different things separately. Okay, now you'll notice that, again, we're at 4 volts. So what happens if we were to put this up to the 6 volts that we were used to? Well, you'll notice that the clock is still doing its thing, but now the circuit is not working at all. And that's because if our logical high is 6 volts, then the clock voltage of like 2.8 isn't enough for the flip-flop to trigger, to count that as a clock. It hasn't transitioned from low enough to high enough, and it doesn't count that. So for this reason, if your clock pulse on your function generator is not getting all the way up to 5 volts or so, then you might not be able to use the full 6 volts here. Okay, so in particular, if we go down to 4 volts, then we see things starting to clock. So one last thing about the scope, again, to get this to work is, especially on these low frequencies, you absolutely have to be on DC coupling. On AC coupling, the triggering would look like this, and it makes it really hard to debug if something's just holding at a high or a low voltage. Then, so imagine that the clock is, let's imagine K here is hooked up to a 1. So now it's just going to be holding a voltage, and it'll be really hard to tell whether that's holding a low voltage or a high voltage. In fact, it's holding high, and that's important to know for debugging, but we wouldn't have figured that out just by looking at the DC coupled, or sorry, the AC coupled signal. Definitely make sure that both your channels are on DC coupling to see this signal working out correctly. So now that we've verified that the flip-flop is working, we don't need to use these input pins directly, or this output pin quite the same. So what we can do is hook up the output to an LED, and let's put that, this is going to be our least significant bit, so why don't we put some space for that over here, and we've got here a 470 ohm resistor. Then we can hook up the LED across that, so that's between ground and putting this as the high. So right now it's not, oh, whoops, missed the thing. Got to put that on this one. Yeah, there's the output. And what we'll do is hook up the input line. For the first one, the first flip-flop, what we need is J always hooked up to high and K always hooked up to ground. So because of that, actually, what we might want to do is just use a low wire for that input. For K bar. And a red wire for the J bar. Okay, so now that that's finally in there, what we can see is that the LED is indeed flashing, but because we've got the two inputs tied to a permanent 1 for J and a permanent 0 for K bar, which means it's always in toggle mode. All right, so that's that first input. The second flip-flop, what we're going to need is J2 is tied to the output of a NAND gate, and K2 is tied to Q1 bar. So this flip-flop is on the other side of the circuit here, so the other side of the dip socket, and we need to hook up the don't clear and don't preset pins number 15 and 11. So those are going to be permanent highs. So pin number 15 hooked up to don't clear, and pin number 11 to don't preset, which is the third one back over here. Okay, so now that flip-flop's ready to go as well. We just need to hook up the clock to that. We've got our flip-flop number 2 hooked up, which is on the other side of flip-flop number 1. And what we've done is we've hooked up the clear pin and the don't preset pins both to high, so don't clear, don't preset, labeled to high. And then we've got this orange wire going across the center here to compare, to set the clocks to be the same for both these flip-flops. Then what we can do is we can set an output LED, let's say to right there, and we'll hook up this output LED using a similar resistor to the output of that one, which is pin number 10. So that one we can connect in there. There we go. And we don't expect that it's doing anything in particular right now because the inputs are not necessarily hooked up. So let's see. One output is let's see, the input K bar is hooked up to the Q bar of the first one. And since the first one is alternating between on and off and on and off, that means the K bar is alternating between on and off. So if we tie the J input to the Q output, then we should be able to force that second one into toggle mode as well, right? However, it's not quite working. So this is a good test. And as I typically do, I actually missed the LED. Right. So now it is doing that sort of counting mode. That's what you'd expect two flip-flops to do. That's not the kind of logic that we're hoping for in this particular case, but it does verify that the flip-flop is working. So it's a good check to do while you're wiring things up. It'll catch if you did something silly like missed the output LED with the resistor. Alright, so now we've got more LEDs in there in place for the second set of flip-flops. So now I'm going to start off by wiring up all the high rails to the different things that we need for this set. So now we've gone and we've wired up the third and fourth flip-flops, a lot of their different wires. What we want to check is that the flip-flop is working. So we've got the J always hooked up to high, so if we hook the not K up to 0, then the third flip-flop with the clock pulse will be toggling every time. To check that the second flip-flop is doing that, we're going to need to, first of all, bridge the clock of this flip-flop over to the clock of the other flip-flop. And the clock on the top rail is the fourth pin from the right, so let's connect that clock up. And then we need to make sure that we need to hook the inputs up to something. So let's hook up K bar to 0 and J to 1, which should force that fourth flip-flop into a toggling mode, but it doesn't seem to be actually toggling there. So let's check if everything is hooked up right about that flip-flop. what do we have for that? We have don't clear hooked up to true. We have the third one from the bottom, don't preset. Oh, so something was loose, and it seems to be fixed now. It might be this don't preset wire. Okay, everything seems fine at this stage. All right, so now that flip-flop is also toggling. The third one is not toggling because we took out that, that wire. So let's hook that up again, just to see if we can get them all toggling at once. Okay. Yep, so the first one and the last two here are all toggling at once. The one here is hooked up to a toggle based on the first one, so it's doing some counting there. All right. If we were to hook up the toggling all in a row, we could use this to make a counter that's moving up, but that's not the kind of logic that we're trying to reproduce for today. So what we're going to need for the particular circuit that we have is to set up the other inputs. So what we can do is make sure that is hook up the inputs that we have that don't involve the NAND gates, and then we'll add the NAND gates at the end perhaps. Okay, so let's see, we need K4 bar to be hooked up to ground all the time. J3 should be hooked up to Q2. K3 bar should be hooked up to Q2 bar. And J4 is hooked up to a NAND gate. Right now J3, because I copied the wrong wires over from the first one, is hooked up to a high, so we'll remove that. And we'll hook up J3 and K3 to the output Qs on the previous circuit here. So let's see, we can take Q, that's Q0, so we'll take Q1 up from here. For these kind of things, we may as well use the larger jumping wires. Okay, so what we need to do is connect from the outputs Q2 and Q2 bar to the inputs J3 and K3 bar. So we're going to connect from Q2 is the one with the resistor on it. We'll jump that over to the J input on the third flip-flop, and then we'll jump from Q2 bar over to the K input on that flip-flop. And now what this should be doing is sort of a counting, but it's on a different clock cycle. So there's a time when this one is going to count up to the next one, but it doesn't require both of the previous ones to be true in order to do that. Okay, so that seems like it's verified. As a clock cycle happens, as soon as this one is on, then it's going to toggle to the next one. Right? So this looks a little bit strange for regular counting here, and that's okay. Great, so the next thing we need to do is wire up the last one. So K4 is permanently connected to ground, so we can get a little ground wire. And we'll need J4 connected to an output of a NAND gate, so we'll just leave that for now. Okay, so there's our K4 hooked up to ground, and J4 we've left for now. The other thing we can hook up is the clock. So the clock on the fourth one is not linked to the other clocks. This clock is linked to K3 bar, so we can hook that up now too. Now we're ready for the last thing that we need, which is our NAND gate. So we'll hook that trusty old NAND gate up in the circuit, and we need two of those. Before we do anything else with that, we'll hook up the high rail and low rail for this set of gates to power it up. Now we're going to need some kind of long wires. So for this type of connection, this is where the jumper wires kind of excel for being a little bit convenient. So we'll take our J2, and we need that hooked up to the output of one of the NAND gates. So let's number these NAND gates. Let's imagine that we're going to use, how about number 4 for this one, and number 1 for this one, keeping in mind that they're numbered 1, 2, 3, 4 on the actual device there. Okay, so let's see, we need number 4's output, which is pin number 11, to connect up to J2 there. So pin number 11, fourth one from the end, 1, 2, 3, 4 there. Okay, so now that NAND gate, the output is hooked up, but the input is not hooked up. So we need the input of that NAND gate to be going over to, let's get a few more wires here. Input of NAND gate number 4 should be hooked up to Q3 bar, which is down here, the same thing that's hooked up to the clock. And one thing that I like to do is have, to make debugging easier later, is imagine that the lower one on the diagram is always input number B, and the higher one is always input number A. So the lower one, input number B, we're going to hook up to that, and the higher one, which is our input number A, input A on this particular NAND gate, is hooked up to Q1. So we need to bridge all the way from here over to Q1, the same one as the resistor. Okay. Next thing we need to do is hook up the very last NAND gate, and you may have noticed that the circuit is actually doing the logic that we wanted already, and that's because when we analyzed it, it turned out that the last NAND gate was redundant. It's always going to be giving us a 1. So with the input floating, we must have left, we must have the same situation as if that other, that J on the third, on the final flip-flop is hooked up to a 1. Now it appears that the J is just floating. What we'll do is we'll hook up the output of that gate, number 1, which is pin number 3 here, to that input. And we need to hook up the inputs to that gate. B is hooked up to the bar of, oh, that's gate number 4. So gate number 1 here is hooked up to the bar of number 2, so Q2 bar. That is over here. Okay, and the other input is hooked up to the same input as the other gate, same as the A input on the other gate, which we can jump to up here. Okay, now as promised, that didn't mess anything up, and we still are reproducing the logic that we expected. So a couple of tips that you probably could figure out just from watching this all the way through. It's a great idea to hook up the common wires, so like the things that are always going to be high and always going to be low, the little wires on all the chips right away, while keeping in mind to space things out enough that you're going to have enough room for when things are done. If you have resistors hooked up to the, or obvious outputs of any kind hooked up to the Qs on the flip-flop, that makes things a lot easier to locate later along the way. You want the clocks that you need hooked up as also one of the one of the first things. And it's a great idea to verify that your logic of the flip-flops is working. We did catch that one very subtle error, that one of the preset pins on this final flip-flop was not really plugged in that well, and that would have been a pretty difficult error to track down if we hadn't noticed that earlier. It is possible to use these large jumper wires. You don't have to use little wires the entire time. I think it's a good idea to keep these for things that you're going to move and things that need to be tested, and that's about what you'd want to do with that. I guess the last thing is to look at the timing diagrams over here on the scope. So in addition to watching things along with the LED, what you might consider doing is hooking up different pins. So while we're first getting started, you can hook up something like this output. So let's say this first one that's toggling all the time. And the last part of the lab asks you to look at what happens as you take the frequency up. So what we can do is increase this by a factor of 10. And you see the LEDs are still keeping up. We can see what's going on with that. The scope is definitely having no trouble with this one. Let's increase by another factor of 10. And now we should be past the threshold. So let's see. Now we're cycling this. Since the LED changes every 2 cycles, every 2 clock pulses, when we're at a 10 hertz wave, then we're getting 5 changes per second. So, but this one is in particular at a 20 hertz wave. So this really is close to like 10 flashes per second. That probably seems like a lot more than 5 to you. It's hard to count at this rate. If we were to slow down to 1 times 10 hertz, now we should be at 5 hertz for the flashes, and you might be able to detect this. These ones are going at fractions of that. So this one here looks close to 1 hertz, and that's because it's going at a quarter of the other rate. Okay, so taking us back up to 2. Now we're at 10 hertz. If we increase this by a factor of 10, then going to 100 hertz should be difficult to see this one, but we'll probably still be able to see the last one flashing. So let's try that. Yeah, so these ones are still alternating between off and on, as we can see with the scope. It is still doing it. It's just that it's past the threshold that you can actually see with your eyes now. The very last one, because that's going at a fraction of the other ones, you can see that. Maybe you can sort of see some different colors in the third one here. But the last one is at sort of a flicker that you can actually detect.
That's it. Thanks for watching. I'll see you next time.